So in the last lecture, we considered the kinetics associated with homogeneous nucleation. Right? We knew that we are going to make a lamella based upon experiments. And we also figured out what the melting temperature of this lamella is as a function of lamellar thickness. And the simplest equation and most profound theoretical result is the Gibbs-Thompson equation. And using data and fitting with Gibbs-Thompson equation, we will get the melting temperature, equilibrium melting temperature. That's one way to do it. But then we showed recent investigations by several groups where the straightforward extrapolation to lamellar thickness going to infinity is not seen, it's not quite viable. Then we had other methods to determine the equilibrium melting temperature. That temperature where it goes to where the growth rate is 0, that means for temperatures above that, there is no growth rate. That means it doesn't grow, no crystals are formed. And that corresponds to an equilibrium lamellar thickness, which is not the extended chain dimension. So that is going back to the original picture here. So it is not going to the full crystalline state, but the equilibrium thickness corresponds to some semi-crystalline state. And that's the equilibrium. Suppose I go here, it's also some finite lamellar thickness, but there is not an equilibrium. That is kinetically trapped because there is a huge barrier here, therefore it stopped there. But if you give some time, it will anneal. Suppose you anneal the system, will go up, when the free energy come down, then eventually it settle down. Even when you do this, if you anneal it for a very long time, the ultimate equilibrium structure will have some lamellar thickness, which is finite, which is not extended chain crystal. That's what we did. And then given that, we figured out what the growth kinetics is, right? And in order to do that, we talked about a nucleation. And if it's a lamella, we took lamella a dimension like this, and then using the same methodology that we did before in the phase separation kinetics, for example, you construct the free energy associated with birth of a crystal nucleus, and then minimize the geometrical dimensions, meaning the free energy with respect to geometrical dimensions. And then from there, you get nucleation barrier and equilibrium. At that time, what's the critical value for lamellar thickness, critical value for lateral dimension for the nucleus to be born, the lamellar nucleus will be born, and then how does it grow? And we're going to talk about the growth today. And then it also gives us a nucleation rate. If this is happening in the manner we think it is, namely in terms of lamella, then the nucleation rate is given by e to the negative some number, which is in the handout, divided by quench depth square and the temperature. And when the quench depth is now defined with respect to this equilibrium melting temperature, that's the quench depth, not with respect to this. See, all the literature that you see, except in the recent years, they will define quench depth with respect to this one, this temperature, extrapolated to lamellar thickness going to infinity. But you really you have to reanalyze the data, experimental data, and you have to define the quench depth with respect to that one, right? So, but nevertheless, independent of how you define it, when the delta T is small, delta T is here, delta T is small, then square of that, right, it's even smaller. And 1 over that is very large number. The negative sign here, exponential of that one is essentially 0. So it is difficult to nucleate. It will take very, very long time in order for it to nucleate if the quench depth is very small. But if the quench depth is say something like 10 degrees, right? Quench depth is 10 degrees or so. then no problem, right? Then there will be a finite growth rate. Therefore, what you will see is, in order to see the nuclei, the crystallization, you have to go to a low temperature, sufficiently low with respect to the equilibrium melting temperature, however way you extrapolate it. Only then you will be able to see the growth of these crystals. This is very important. It's not good enough for the temperature to be below the melting temperature, equilibrium melting temperature. It has to be substantially low according to this classical nucleation theory. And this is verified. You can have small modifications due to fluctuations, etc. But in general, this is a good concept, and that is a rule of thumb to investigate polymer crystallization. All right, now let's go to today. We are going to talk about how does this lamella grow. And I reminded you, based on what we did in the, well, almost 4 lectures ago, 3 or 4 lectures ago, about nucleation, homogeneous nucleation in multiple dimensions, in 3 dimensions, 2 dimensions. We even talked about an one-dimensional growth like amyloid. In a one-dimensional growth, you do not have a nucleation barrier. If you go back and look at your notes, right, you'll see that for, say, if you take only, you take one object, say protein, another protein molecule, and then you let's try to assemble them like in a one-dimensional rod, chain, fiber, and there is no nucleation barrier for that. And the kinetics of that process, how amyloids form, is different from the way we discuss here, right? And that you have to look at papers in the literature, right? And that's it's an important problem, right? As you know, from preventing human diseases, you know, we want to get rid of formation of these fibers and their associations. So we are not going to talk about that in this course, right? But on the other hand, if you do a 2-dimensional nucleation, then the nucleation rate will have a different formula, e to the exponential power minus some number divided temperature times supercooling, quench depth. This for 2 dimensions. We knew this even before a polymer field was practiced, okay? Because this is a very general result. Nucleation has been, around for a while. So this is a very simple prediction. If I have a homogeneous nucleation in 2 dimensions, this is the law, okay? Let's keep this in our mind and go to our present problem. Our present problem is, how does a lamella that is grown, that's born, how does it grow? So I have let's assume I have a lamella which is already born by a homogeneous nucleation. That is the first primary nucleation process. So here I have the stems, right? Here, you know, there are stems here. So this is a lamellar thickness L. Okay, there are stems here like this. This is the lamellar thickness L. And then this is a fold surface. And because the chains are folding back and forth, very much like what Mr. Stokes told us in the 1930s, right? So the surface free energy and the fold surface, let it be sigma F, fold surface free energy. And similarly, in the lateral surface, sigma L, that is the surface free energy per unit area in the lateral surface. So now what I like to do is I like to think about how a chain like this, right? In a melt, suppose I have a melt like this. How does this chain come and grow here? That's the question. How does this lamella, the lateral surface, how does it grow? Because we know that this L is fixed. by equilibrium, it reaches some certain value. Even if you anneal it, it'll reach some value. The question is, how does it come and attach here? And on also here, lateral surface. That's the primary question we are interested in. Okay. Now, this is an ongoing question. Right, very early on in 1960s, there was a very nice theory. That theory is called Lauritzen-Hoffman theory. Right. See, what they did is this. They wanted to adopt, they adopted a small molecular situation, because they knew how nucleation will happen, right, classically. There is no entropy in here. No entropy. That's in no conformational entropy. I should have written, of course, there's always entropy, but no conformational entropy. Okay. Right. So how did they do? They made the following imagination, which is, okay, so I have a surface like this. Okay. This distance is lamellar thickness L. Let's say this lateral dimension, let's say LP, let's assume that. Then what we are trying to do is we are trying to bring this polymer chain in. They imagine when the chain comes here, the chain is broken into stems. Imagine. The chain attaches like stems. That means what? As soon as the chain comes, it breaks up into something like a stem like this. So let me draw. This is my growth front, normal to that, like that, right? And then like sorry, I made a mistake. Like that. So yeah, first a stem is made, right? The length of the stem is same as L. Let's say when the chain gets deposited, let's say this distance is B, right? That's the distance between one polymer segment and another polymer segment. Assume it's a small b. They used a classical argument, the macroscopic ideas, right? B. And also let's say this distance is A. Okay, they deposit a stem which is a parallelepiped. The length is L, right? This length is L, right? And then in the direction where it's growing, so let me call this direction to be the growth direction. And the growth direction, let's say the growth rate is G. Growth rate, right? That's the real growth rate. Then when it deposits here, you know that it's a lateral surface here. That means the other stems will also come and fill this layer, the growth layer. And that happens with some G, which is called a spreading rate. It spreads. So this is a growth front. A stem comes and attaches here. And then the dimension of that stem is the height is L, and the thickness in the direction of the growth is B, and then the side width is A. Right. Okay, this is for the first stem. For the first stem, then let's calculate the free energy of the first stem. Exactly the way we did before, right? In here, we constructed the free energy, right? So similarly, let's write the free energy to make the first stem. So to make the first stem, let me write again in red, delta G1 is equal to negative, right? What's the volume? Volume is A times B times L. Negative A, B, L, and delta mu. That's the energy, right? And then let's look at the cost in making the surface. Look, before I deposited this, right? I had a surface area like this, which is A times L, the surface, that is replaced by a new surface, right? New surface with the lateral surface energy. So since I created a surface and then got rid of the previous surface, there is no gain. Because initially whatever I had here is replaced by the new one, therefore there is no change. We got that, right? So the surface energy comes only from these side faces. One is here, another is on the other side. The surface area of this is B times L, okay? And creating a new surface is costly. So I write plus BL, plus sign BL. And then what is the surface free energy per unit area? Surface free energy per unit area is here, sigma L, right? So that's the sigma L. And as I mentioned already, there are two surfaces, one here and the one on the other side. So I write it 2. Okay. So that is the cost in free energy or gain in free energy, depending upon how you look at it, depending upon these different values, right? For a deposition of the first stem. So this is for first stem. Now let's look at the second stem. For the second stem, let me use a different color. For the second stem, let's assume it goes that way. Okay. For the second stem, let's write the energy. Okay. Delta G2. What is that? Okay, again, this surface, right? This surface is the same as before, right? This surface as before. Okay, it was blank there, that's replaced by this new surface, which has same surface energy. And then this surface energy, right? There is no interface there. So when I go behind this green box, the surface area BL on the other side, right, is the same as what I had on the other side of this red box. Therefore, there is no change. So in terms of this lateral direction, there is no change, right? And also in this direction, there's no change. But, right, these people cleverly imagined that there is going to be a chain, tight chain between this red box and green box. There's going to be a tight chain like this. Okay. Similarly, at the bottom, right? And then they argued, okay, so what is the free energy? When I put the due to this, what is the free energy to create that surface? That we know that surface free energy is sigma F per unit area on the full surface. So I'm creating a new surface here. So the cost is sigma F. And then what is the area of this? The area is, right? What is the area corresponding to this one? Any comments? Okay. It is A is this direction and B is that one. The area is AB. There are two surfaces, one AB there, and at the bottom of this, there is also an area. So it's a 2 times, right? So I will have plus 2AB sigma F, 2AB sigma F. That is the free energy cost to create the surface. But what is the gain? The gain is, the volume of this is again L times B times A and delta mu. So negative, same as before, AML delta mu. So this is the energy to create the second step. And then you can repeat this process until the chain gets deposited. Then as you can tell, this can happen sideways, lateral, the spreading way. This is, when I do this, every time I put a stem, I'll have this energy. Either I put it that way or in this way. But at the same time, I can also put a stem in the next layer. If you want to put the stem in the next layer, and I will use this idea for system. So therefore, you can create a free energy landscape for growing this lamella. You can create this, the whole landscape for one chain to get deposited, second chain to be deposited, and third chain to be deposited. Okay, given this, I'm going to write down the landscape. So let me draw free energy. This is a number of stems. Not the chains, number of stems. Let's start with, for example, let's start with a free energy here. Okay, that is 0 stem. And then the first stem is here. This is 1, right? 2. We did so far only 2. And what we have shown is, okay, with respect to this, the first, to deposit first stem, this is our free energy. Depending upon choices of A, B, and L, and depending upon sigma L, whether you measure it or take it from, literature, computation, so you know what sigma L is, and delta mu. Delta mu is related to the quench depth, right? If you do that, I'm giving you as an example, you will have some value here. This one. This is my delta mu. And then when I do the next calculation, delta second stem, the only difference here is between sigma L and sigma F. Okay. And it turns out the sigma F, at least this is an assumption, sigma F is smaller than sigma L. Because going back to this argument, if a sigma F going here is smaller, then it's easy to make that surface more compared to sigma L. Given sigma F and sigma L, right? If sigma F is small, then it's easy to make that surface compared to the lateral surface. That's the reason why we have lamella. So the very fact that a lamella is formed in our systems means sigma F must be less than sigma L. This is still a question that's being pursued by all of us. Our host, June Fang, and her colleagues, they are working on this right now. How to compute sigma F compared to sigma L so that we understand why lamella are born the way they are born, right? Because it must be so. If you see lamella, it must be that sigma F is less than sigma L. So Lauritzen-Hoffman used this information. They knew that it was going to form a lamella. They used this information. Therefore, the free energy of the second stem has to be smaller. So it's going to be something like this. Smaller than the free energy cost to make the first stem. Then they made an assumption. The assumption is, or they imagined, right? In order to go from here to here, there is a barrier, they assumed. Okay? In order to go from here to here, it's not going to go just like this because we know nucleation process has a barrier. All right? So here is the first stem being deposited. And in order to go from here to here, there is going to be a barrier. So they assumed a barrier like this. Okay, so how did they do that? And I told you that the delta G1, delta G1, right? Here is a delta G1, I'm rewriting it again, minus ABL delta mu plus 2BL sigma L. What they said was, okay, the barrier is going to be for the first stem, delta G1 star, if you like, is going to be, I'm going to put a parameter, a portion, not the whole thing. The gain is only a portion of this. You know, the total gain is going to be resulting into this. If the gain is only partially, when the stem is attaching, it's not attaching completely. So there is some local disorder inside this box. And therefore, the gain in energy is not completely full. So they put a parameter, simply minus psi, a parameter ABL delta mu plus 2BL sigma L. So they introduced this parameter. Okay, this is actually a parameter, and they called this to be apportioning parameter. And there is no fundamental understanding of this. We all know that there must be a barrier, right? We think it should be a barrier, right? It's a natural process. So now you look at lots of parameters here in this theory already, right? And then it settles down to here. So this delta G1 star, okay, this is a delta G1 star, and this is delta G1. So this is delta G1. This value is delta G1 star. Okay, there is a barrier, it comes down. Now for the second stem, right, it is going to go from here to here, right? That's the way it's going to go. Again, they assumed that there is going to be a barrier. So similar to what I had before, delta G2, I'll write it again. Delta G2 is, oh, sorry, I forgot already. Delta G2 is minus AB L delta mu plus 2AB sigma F. Then they put, for the barrier, delta G2 star, they put negative sign, same value, same parameter, ABL delta mu plus 2AB sigma F. That's what they do. This is again the same apportioning parameter. They use the same value. So the consequence of this is Okay, there's a barrier here and comes down. And then this process gets repeated, right? The process gets repeated. Then I go to the third one, it will go like this and come down. And then fourth one will go like that and come down, etc., etc. And this goes on and on. So this is the way they constructed the free energy landscape. So once you have the free energy landscape like this, then you can do classical theory, because you can look at the rate with which, right? The rate with which it's going to go up. Like for example, right, there's growth rate. So to go to the barrier, this barrier, let's assume A0 is a rate. Okay. And then after first one, because you can see there's a big difference between this goes from melt in front of the growth front to deposition of the first stem. But this is a different case. Already one stem is there, right? Therefore, this growth rate will be different. That is growth rate going that way. And then to go back, that's the growth rate, right? That's the growth rate for that. This is the growth rate here. This is the growth rate to do that. And similarly, to the growth rate to go backward, on and on and on. And these are dependent upon energy differences. As you know from chemical kinetics, the rate is related to the difference in free energy between the final state and the initial state. So you can write given these expressions that I have written in here for this model, you could write down all these growth rates. Okay, and then you look for the steady state. How does it grow in the steady state? And I will not derive this because it's a derivable. It is given in the handout. If you are interested, please go and look at them, look at the derivation. The growth rate turns out to be, right, something like I can calculate the steady state growth rate. Lamellar thickness. Yeah. So I get S of L. Okay. We can calculate this. And it is all in terms of the various parameters. How many parameters there are? Let's count them. I do not know A. I do not know B. We know L, right? Delta mu is our control variable. Sigma L is a parameter, right? We do not know that, right? And we can put some reasonable values, but it's still a parameter. Sigma F, again, a parameter. We can put reasonable values. You can keep on counting them, right? The 1, 2, 3, 4, so far. And then there is also delta mu. How do you choose melting temperature there? Right? We do not know that because delta mu, as you know, is quench depth, delta T, and there's melting temperature comes in there, right? Equal melting temperature, which we do not know. That's 5 parameters. Then we have 6 parameter 6. Okay. So you'll be able to write these equations for A and B in terms of these parameters, and then that comes these values, S of L, some function. The total flux, right? Total flux means the total rate of deposition, right? Let me call that to be S. Total flux is given by S of L, right? Summation over all possible L's. Okay, you allow the lamellar thickness to go to infinity, but as you know, it can grow only if it's larger than the initial lamellar thickness, L0. We know that, right? L0 is, we worked it out before. L0 is, where was this? Here. Even here, right? Oh, here. L0 is, if you plot free energy, I think it's in here. Oops, sorry. Where did we do this? We did this before. Delta G Did we not do this? I thought we did this. Okay, delta G. Oh, here it is. So delta G, if you do this, let me go to this. Delta G is given by this, right? Then let me plot this with as a function of L. Delta G, I plot as a function of L, right? When L is zero, I have this positive number, 2a sigma f. So it starts from there. Then when you increase L, because the negative sign, I'll have a straight line with a slope like this, right? And then where do you get to zero? Because only when delta G becomes negative, I'm going to have a lamella. So this let me call L0. When does that happen? That means when delta G is zero. You solve this equation, A is a common factor. L0 turns out to be, right? Therefore, L0 is equal to 2 sigma F by delta mu. That's your initial lamellar thickness. Okay? Because that's the time where delta G becomes zero. So L0 is equal to 2 sigma F by delta mu. And that comes directly. As soon as you say it's a lamella, that is me. And this lamella is not stable if a lamellar thickness is smaller than this. So going back here, that L0 is what I just said, right? That's equal to 2 sigma F by delta mu. Okay. Okay, so you calculate S of L from these kinetic equations and then sum it up, that gives you total flux. What is one of the very nice things about this theory is it does not tell that there is a given lamellar thickness. It says, all that it says is the lamellar thickness is higher than L0. And it has to be, that's all it says. Then from this S, we can calculate the preferred lamellar thickness. What is the, what is the optimum lamellar thickness that will happen? That can be calculated by the following formula, right? The optimum or average lamellar thickness, oops. Now I'll do this and then I stop here. Just give me 1 second. Average lamellar thickness, let me call this the L star. That's equal to, the usual thing, right? Take the first moment, average over L. This is dL, 0 to infinity. Basically, it should be L0 to infinity, right? And then with respect to the steady state value, divided by dL, L0 to infinity, then SL. So you calculate this from kinetic equations, put this in, you get the total flux for all values of L as a function of a lot of things. That's the total flux. But in terms of getting the average thickness, you take S of L for a given L, and then whichever whichever thickness which makes it the fastest growth, fastest flux will contribute more. Higher flux will contribute more. Based on that, you get the average lamellar thickness. Okay. If you do that, what you get is this is equal to L0 plus some extra value. Okay, and this is calculable. Calculable, right, from those 6 parameters, the various parameters we put in. Calculable, okay? I think I should stop here and let's take a break. So the calculated average lamellar thickness has this minimum lamellar thickness L0 given by this formula, 2 sigma F by delta mu, plus an extra bit, because after the initial lamella is born, it's growing. Due to the growth, there's going to be some appropriate lamellar thickness at which the growth rate is optimal. And then what they predicted is this delta L is proportional to the full formula is given in the handout, but it's proportional to a factor which looks like this: 1 divided by 1 minus A, that's a parameter, psi is a parameter, delta mu is the quench depth driving force in terms of one parameter, at least two parameters, 2 sigma L. And then other terms, okay? There are lots of other terms in here, but the key term that I like to focus is it is inversely proportional to 1. There's a negative sign here, right? All right, and delta L is extra thickness, right? Delta L is going back here, whatever we had to begin with L0 plus some extra thickness. That is my, right? That's the extra addition due to the growth process. But the problem here is the following. Let's imagine what happens if delta mu is equal to 2 sigma L by A times psi. What happens? Right? If I have 2 sigma L by A psi is same as delta mu, then this is 1. With this 1, I have in the denominator 1 minus 1, that is 0. Delta L goes to infinity. Delta L goes to, delta L goes to infinity. Okay. And that is very strange, because if you choose the parameters, or it could be experimentally, it could be sigma L and A could be such that, and there would be some quench depth where suddenly the lamellar thickness will go to infinity. Okay. And this is a problem. Okay. So this is in the literature is called delta L catastrophe. Because that's a prediction. Okay, this is a prediction of a large number. This is not observed. People don't see that. Everything is smooth. The lamellar thickness as a function of quench depth, it's all very smooth behavior. There is no sudden catastrophe, right? But nevertheless, this is one of the predictions. Please notice that the calculation of L star is not based on equilibrium arguments, because this is a kinetic theory. It is based upon calculating the fluxes and putting them in here and constituting the optimum value. So this is a kinetic theory. Based on this, you calculate analytically, you calculate the lamellar thickness, and then in addition to the initial lamellar thickness, there is a calculable change in thickness, positive value, but that becomes infinity at a particular choice of delta mu, which is called delta L catastrophe. That is a problem with the Lauritzen-Hoffman theory, right? Fundamentally, there is an issue here, and that's the prediction. Now what we'll do is, okay, let's keep that in mind. And now let's go and look at the values of the growth rate. Let's go and look at how the growth rate occurs, right? What is G? What is that? But that's what we are interested in, because that is what we measure. Experimentally, people have done beautiful measurements to figure out what the growth rate is. How does that happen? Now, the calculation is a paper and pencil calculation, so we can do everything, right, as detailed in the handout, and also written in many review articles, and also in their own original papers, right? It's all well documented. But in the interest of time, and also in terms of having a general idea, I'm going to give you some key conceptual results, and then give the formula. Okay. This takes us to possible scenarios. Again, I'll go back to this picture. So there are two ways the growth takes place. One is the growth rate G, right, going in a lateral direction. And then there is a spreading rate, small g, which is corresponding to how they spread around on parallel to the growth front. So this is the growth front. How does the growth front to propagate with certain velocity? And that's given in terms of this capital G, growth rate. A little g gives me spreading rate. Okay, so these are the two quantities we can calculate from this model. Let me focus on G. When I look at how the growth rate takes place, it depends on two features. One is how quickly a new stem gets deposited. Okay, if a new stem gets deposited, the red stem gets deposited very quick, then I'll have a red stem and next to red stem. On the other hand, if the speed with which the green stem gets deposited, then it's going to spread, right? It's going to spread sideways. So depending upon the relative values of which is faster, whether spreading rate is faster or the growth rate, growth front rate is a faster, or a nucleation rate is faster, right? We are going to have different scenarios. So instead of the G is a total growth rate, right? For the red one, let me write down the first one, let me call this to be I is nucleation rate. Nucleation rate to create a new stem. So I is a nucleation rate, right, where to deposit this red stem onto the growth front. Okay. And G is a spreading rate. Okay. Okay. So incidentally, this whole process that I'm talking about, which is the Lauritzen-Hoffman theory, is called a secondary nucleation or secondary crystallization. Remember, the birth of the lamella we call the primary nucleation. As I told you in the last lecture, this is a secondary nucleation, right? This is a secondary nucleation. So that's what we are talking about. This is secondary nucleation, right? So depending upon I and G, we can imagine lots of possibilities. Let's imagine first. Let's imagine how it looks like. Right? Just conceptually, right? So let's assume this is my growth front, right? This is my growth front, and let's assume the I is, let's assume, okay, I is a smaller, G is much greater than I. I is a nucleation rate, and G is a lateral, so the spreading rate. Okay. See, if I, first of all, you need to have a stem, right? So you need to have a stem like this. First, you have to have. That's your first case, right? So if I have this scenario, G is greater than I, then my situation is going to look like this. As soon as, okay, so I start with this. As soon as I have G larger than, as soon as this is made, then it's going to spread, right? It's going to spread with the second stem, I mean, laterally spreading, right? So then what I'll have is, I'll have very quickly, I'll have like this, like that, like that, like that, like that, like that, like that, and on and on. That's what is going to happen. If this happens, we call this to be regime 1. Okay, this is one possible scenario. We call this to be regime 1, first regime. Right. For the first regime, we can calculate the value of the growth rate. Given this, using all these formulas we found out, or we constructed, we can calculate this full G. Okay, so let's do that. And that full G in the first regime, apart from all the prefactors, right, goes like e to the I'm going to write something like this, some number here, which I'm not going to write down, which is known. Okay. E to the minus kg, I'll write down for the first regime, divided by t delta t. Please notice it, delta t, e to the minus 1 over delta t. This comes after doing all these calculations. But you know that result already because you don't have to do any complicated calculations, right? But just a very simple contraction of two-dimensional growth, you can get e to the minus 1 over t times delta t, right? Of course, the number depends on these details, and that's what happens. The number that you get here depends on the details. Okay. And then what is this a kg1? The kg1, they calculate kg1 is equal to now 4 times B, you know, B, we define B, sigma L, sigma F, right? Equilibrium melting temperature, Tm0 divided by Boltzmann constant times delta H. That's, you know, this is, you should look very familiar to you because for two-dimensional growth, you know, the nucleation barrier would look like this, apart from this B and 4, right? And that's what you get. Regime 1, you get this. So you have, again, once more, universal behavior, that e to the minus 1 over delta t. Now let's go to next case, right? The next case would be regime, let me go to regime 3, okay, to make regime 3. Regime 3, let me write down here, regime 3. This corresponds to the other extreme, that is I is much greater than G. Let's draw a cartoon. I had the first stem, right? And then if I is greater than G, as the time goes by, what will happen is, oh, it will nucleate here. First stem will come here, another one will come here, another one will come there, another one will come there, another one will come there, and on and on. Maybe it'll come here and maybe come here like this. That's what will happen. Okay, instead of spreading, and every now and then, of course, you'll have some spreading, but this is much greater than G because the nucleation is much faster. Nuclear system is much faster, so that's what will happen. Right. If you do this, right, if you do something like this, then what happens is, the growth rate, G3, I'll write down G3, is a number, a different number, right? And remarkably, right, I'll write on Kg3 by T delta T. Okay. And what is the Kg3? It turns out Kg3 is same as Kg1. If you do the calculation, that's what happens. Okay. But the prefactor is different. Okay. The prefactor is different from that prefactor. Now let's go to the intermediate case of regime 2. Okay. Meanwhile, I must say, it doesn't mean there is no spreading. Still, G is not 0. G is finite. So still, every now and then, you'll have, say, something like this. Right? Every now and then, you'll have some little bit of spreading. Now let me go to the intermediate case of regime 2. In regime 2, right, we are going to say, let's say the nucleation is a little bit higher than G, but not that high. Because if you don't have this one, then it will not make a new layer. So you must have some nucleation rate. If you do that, then you started from this, right? Then there is a competition between both the spreading and the growth, right? So I'll have next one, I'll have say something like this, something like that. Then I'll have, say, something like this, and then maybe next one will something like this, and then maybe nucleate like this, maybe nucleate like that, and then I'll say something like this, and on and on. You know what I mean? So on and on like this. If you do this, the calculated predicted value of G2 is equal to another number if you like, e to the minus kg, same structure for the second regime divided by T delta T. And what is a kg in the second regime? That turns out to be 1/2 of whatever we had here. Instead of 4, I get 2. Instead of 4, I have 2. Okay, so 1/2 of kg1. That's the theory. These are the predictions of Lauritzen-Hoffman theory. So that means what? That means we expect. So if you take this, apart from all these numbers, right? If you expect these results, then if I plot a logarithm of G, because this is exponential decay, logarithm of G versus 1 over T times delta T, right? I will have one slope, negative slope, and the slope will be kg1 for the first regime. For the third regime also, right? For the third regime also, I'll have the same slope because kg3 is same as the kg1, same slope. And then in regime 2, the slope will be half of the slope that we have in regime 1, regime 3. And please remember, we already talked about the nucleation rate, right? If the quench depth is, as we talked about here, when the quench depth is small, right? Quench depth is small, the nucleation rate is very high in general. That means you have to, right? So that means if you want to have very large nucleation rate, the quench depth should be strong. That means that's happening at a lower temperature. So what I will do is I will plot logarithm of, based upon the 3 equations, I'll plot a logarithm of G, the growth rate, as a function of 1 over T delta T. Okay. When I say delta T, if it's a large, I'm in regime 3, right? So the prediction is, right, the large means I'm in here. That's regime 3, he'll be regime 1. So the prediction is this. So I'll have, I didn't draw this properly. I have the slope here for regime 1. And for regime 2, I have a slope which is half of that. This is regime 2. And regime 3, I'll have the same slope, it will be like this. That will be regime 3. So there will be 2 breakpoints. So these are the clear predictions of Lauritzen-Hoffman theory. The prediction is that if you plot growth rate as a function of 1 over logarithm of growth rate versus 1 over T delta T, I'll see 3 straight line portions for regime 1 and regime 2, regime 3. And more remarkably, the prediction is the slope here should be exactly half of the slope here. Okay, these are the predictions. Now let's go and check. Let's go and check the reality. Check with the data. Okay. But please recognize, in checking with the data and comparing with the theory, there are lots of parameters we have to play with. That's what Lauritzen-Hoffman did. Hoffman particularly, he did. Right? And let's look for a comparison between experimental data and the predictions. For that, I'm going to go back to the handout that I sent you folks. Let me go and look at this one. Okay, so that's a prediction. Logarithm of G whereas 1 over T delta T will have first regime, second regime, third regime. And here are the data. I have taken care to show you give you references coming mainly from Hoffman, right? And this is again 1 over T delta T, logarithm of G. Please look at this. This is regime 1, right? And there's a clear breakpoint to regime 2. Regime 2, that's the breakpoint. And that slope is half of this slope. If you read that paper, that's what they will claim. Now let's go to the next one. What is the transition between 2 and 3? Okay. And people believe, again, it's a Hoffman and collaborators, various people. This is, they see some deviation. This is from regime 2. Regime 2 is this one, this behavior. And then when they go to the deeper and deeper quenches, they wanted to see this break, right? And they claimed that there is a break there. And they drew nice lines like this, but the deviation here is this, okay? And this is what is reported in the literature. And if you look at the caption, there are lots of parameters, as you can tell. You have to choose a lot of these numbers, right? So that's how they found evidence, so-called evidence for regime 2 to regime 3, and it's your call. You know, as an independent scientist, you should not believe everything that instructors say and what the papers say. You have to go and look at them and come to your own judgment about how good they are, etc. If you take here, I don't see any transition, right? For example, right? So we have to do that. Okay, let's go to, we'll take the same data, right? We take all this data, right? And then Hoffman, right, put them into one picture. He showed that, okay, according to the predictions, let me draw you that. According to the predictions, he and his collaborators showed that, again, logarithm of G, right, versus T over delta, 1 over T times delta T, regime 1, regime 2, regime 3. This is for polyethylene. For polyethylene, right, the breakpoint between the regime 1, regime 2 polyethylene melt is 129 degrees Celsius, and the breakpoint between regime 2 and regime 3 is 121 degrees Celsius. And in their fitting, and also based on the previous extrapolated value of equilibrium melting temperature, they took something like 141 degrees Celsius. 141, you can choose 141 to 143. Right? That's a kind of melting temperature, equilibrium melting temperature they chose, because that's important. What number you put in here, that's important, right? Now, taking the same data, right, actual data, experimental data, and without using any of the parameters, you simply plot the growth rate versus temperature. Don't do any analysis of it, just plot the actual data. This was done by Strobel and collaborators. And right. And if you do that, this is growth rate, logarithmic scale, regular temperature. There are no regimes here, right? You don't see any breakpoints in here. It's a smooth curve, the G versus T. And they claimed, right, this is this paper. Regime 2, I think I've given a reference above, okay? What they claim is that they all ended at 131 degrees. Okay, here they use 141. I hope I didn't misspeak. Here it was 100, the extrapolated value was 141 to 143 degrees. Here what they claimed, yes, the growth not claimed, they observed from the data is 132 degrees, between 131 and 132. Nothing else happened. And they also showed that that's your zero growth rate situation. The growth rate is zero. It doesn't happen. So this means two things. Number one is, right, let me go back here. Number one is the picture that we talked about. So that's the growth, zero growth rate. Remember, this is So it is not TM0, that 141 to 143 degrees that Lauritzen-Hoffman used in showing, or Hoffman used in showing the existence of those three regimes, right? And Strobel did not use that number. He did not do anything like that. Just like he showed as an alert to the community, if you do these things, you get only this curve. Therefore, the question turns out to be, what are lamellar-Hoffman stems? And what's going on? How come the raw data, don't show the three regimes? So what is happening? So this is the modern question. We are at a situation of trying to figure out, having figured out a little bit of, we have some good ideas, meaning the literature is very clear. So this picture is the classical picture, which is analytically doable. That's one of the wonderful things about this picture, right? You don't put in a computer and wait what happens, right? This is paper and pencil calculation. And those predictions don't seem to be borne out in general by the direct analysis of experimental data. Now let's go and look at what are these stems. So this is where computer simulations come in, right? If you do that, here is a paper from my own group sometime back. So you grow a lamella, which we know that is born, right? And then let's watch how it grows. So if you look at how the chain goes and attaches, it doesn't go like a stem, the way we imagined in the Lauritzen-Hoffman theory. It doesn't go like a cylindrical box, right? Parallel pipette box, and then goes and attaches one stem at a time. There's lots of entropy. They just go in here, right? And then once it gets attached, you can watch in movies how the stem is born. There is no such a stem, right? Parallelly, they get deposited in a random ways at the growth front, and then they adjust themselves. The monomers know that they have to be registry. They have to register at the growth front, and eventually something like this, a folded structure will be formed at the growth front. Incidentally, the Lauritzen-Hoffman theory was meant only for solution growth, not for melt. So these simulations for solution conditions. But remarkably, if you look at the free energy barrier for the attachment of the segments, you don't see any barrier. This is a free energy landscape. The calculated free energy landscape looks like this, because this is more like absorption. Okay, instead of the picture that I showed you, this picture, instead of that picture, there is a barrier here, and the whole theory is based upon barrier, right? Based upon energy, no conformation entropy, just adopting small molecular cases where only energy is taken into account, right? That's what this theory was done. So now when you go here, when you calculate the free energy barrier, there is no barrier. It's more like an absorption followed by registry. So that means we have to look into, but we know experimentally, this goes like e to the minus 1 over t delta t. We know that, the growth rate. So what's the origin of this? And as we all talked about already, a conformational entropy plays a role at finite temperature. If you do that, right? So imagine I have a growth front here and many chains that come in here, particularly in a melt. So what happens is if there is no barrier, right, the growth rate is dictated by the rate of adsorption, and the red term is the rate of desorption. If you do this for a given concentration of the polymers, for example, if you do this, G versus temperature will go like this. That's the curve, right? If there is no barrier at all. But we do know that there is a barrier. Why do we have barrier? Because when the chain is stuck here, it is not easy for it to go and directly attach, cannot directly absorb. There are going to be entropic barriers or free energy barriers coming from lots of possibilities like entanglements, right? And for it to, right, when the red is already there, blue has to go in here and participate together or displace them. There are lots of reasons why there are going to be barriers. Those barriers are coming from entropy. And if you have a barrier, then there'll be this formula, which is generally true for small molecular crystallization, large molecular crystallization is generally true. When you do this, what happens is you get a term, extra term, where this D in is diffusion coefficient inside the layer, right? And this capital D is the diffusion coefficient in the bulk. Okay, they don't have to be the same because of non-equilibrium conditions. In fact, I must advertise the work that Pang and Fan Pang and Jun Pang are working along with their colleagues, and also we are all working together, right? Trying to figure out these intrinsic details of this particular mechanism. Right? But in principle, conceptually, there is this blue term, which has this Arrhenius term, e to the minus some number which we have to figure out, T delta T. Particularly in a melt, right, there are going to be considerable amount of confinement to free energy due to the polymer chains not taking all possible conformations. That creates a barrier. So if you do that, then you get this law, because this term, the blue term, dominates over this bracket term. When this dominates, then log G versus 1 over T times the delta T will be a linear line, straight line. So this is still going, the details are being pursued, but in principle, that's where the barrier comes from. Right. So now let me, oops. Okay, I think I'm done here. I think, so let me go back to the final argument, right? Check with data. So what I'm going to say is, I'm going to say, checking with the data, no clear evidence clear evidence for regimes. Number one, right? Number two, no clear evidence for barriers from only enthalpy. Okay, only have, if you, without any entropy, you will not have any barriers. Okay. Now, then suggestion is, our latest theory is crystallization kinetics is controlled by entropic barriers. Details of these for this problem are presently addressed. People are working on this using experiments, simulations, theory. And that's where I like to stop this discussion, right? And then I like to take questions. So I'm going to stop sharing this